So we saw that for the Anderson model, what did we see? So h omega equals minus Laplacian plus v omega. Well, if you define the density of states, right, then you have, so n is the integrated density of states, then you have n of e minus e prime, which is bounded by some constant, times mu of, well, another constant here, it was 4, I think, mu of e minus e prime. Let me put an absolute value, where what is mu? Where, so v omega, this is omega n delta n n prime, since the matrix, diagonal, and where mu of x is the supremum, or mu of epsilon is the supremum over x in R of the probability that omega zeros, we assume that the omega n are IID, omega 0 belongs to x plus epsilon. Right, so this is what we saw yesterday. So this is actually a consequence of Wegener, right? So this is, and Wegener is just the other thing, is that if you look at the expectation of the number of eigenvalues of h omega lambda in e prime, this is bounded from above by constant times the volume lambda times mu c e minus e prime. Right? That's the result that we proved for the Anderson model. Now, so it tells you that given some energy E, right? Well, if you look at the small interval around E, then there are not too many eigenvalues in these intervals, right? But if you take, because this is uniform in E minus E prime, right? If you now take the distance between E and E prime to be really small, right? For example, assume the omega n admit a bounded density. Then obviously mu of epsilon is going to be bounded by a constant times epsilon, right? Mu of epsilon is going to be bounded by a constant times epsilon, right? Just compute probability of bounded density, you get that this is. And so in this case, what you have that if epsilon is less than 1 over, so what we get is that the number, right, of these eigenvalues, the number of the eigenvalues here is going to be less than c epsilon times lambda. So you see that if epsilon times lambda times c is less than 1, well, the number of these eigenvalues, the average number here, is going to be less than 1, right? So actually this gives you an estimate, which we already wrote, on the probability that there is an eigenvalue, right? This gives you an estimate on the probability that there is an eigenvalue. And you see that this probability is going to start to be small if the length of epsilon, so if epsilon much smaller than 1 over lambda, well, with a good probability, no eigenvalue for h omega lambda in e minus epsilon, e plus epsilon. Right? This you have with a good probability. And that's going to be a useful thing to know. I'll tell you why at the end of, actually, it's going to be the second half of today's lecture. Okay, now we can ask if, can one expect, so here we have two things. I'm going to call this C-like continuity, right? This is some continuity of the density of states. And you're going to have Wegener, right? So of course we have in general, we always have Wegener implies C, right? We always have Wegener implies C. Okay? But in general, there's no reason why one should have the reverse one, right? That's not obvious that if you have it, as I explained, in the limit, you may very well have that the density of states has some regularity, but if you look at what's happening for finite volumes, the situation can be much more complicated, right? Meaning that you could have a few eigenvalues, right, that remain fixed in some way, right? Much more than the bulk of the eigenvalues. Okay? So that's one of the things. So the other question is, so we proved this for the Anderson model. For which models is this true? Right? What are the results for more general models or different ones? So this was actually, there has been a lot of work on this in the last 20 years, right? So so there is the general result of Bourgain and Klein that I already mentioned, right? Where they prove that for continuous models that actually do not really need to be ergodic, but I just take ergodic I just assume that it's ergodic so that the density of states exists. One has in dimensions, though this is dimension 1, 2, 3. Not in dimension 4 that proof doesn't work, but one has that n of E is log Hölder continuous, which means that you have an inequality of this type, right? But really it's here the inverse power of a logarithm. Okay. Now, but yeah, so that's correct. But now you want to, so you see, as I explained yesterday, the main difference between this one is that this relies essentially on the random potential, whereas this one relied on the Laplacian. It used, right, properties of the PDE. And the right thing to get is that you're using a mix of the two. So there are results where you get, so you see this log Hölder continuous, the result that they get, it's always log Hölder continuous, but their result does not improve if, for example, the random variables have a distribution which has a density, right? It does not improve, okay? So, actually there are a number of questions that are related to this. So what can I say? There are a number of questions. So, for example, for the continuous Anderson model, one can prove that. So it says h omega equals minus Laplacian plus the sum of omega gamma v x minus gamma. Let's say gamma in ZD, and you can add some periodic. ZD periodic. Then, with Combe and Hislop, we proved, so we just need one thing. So omega gamma is just as in the Anderson model, and we need that V be non-negative, right? Actually, it could be non-positive, works the same way. and V is not identically 0. Right? If you take V non-negative and not identically 0, then in a paper in 2000, I think it's 2007, we proved that C and W hold, right, for such a model at all energies. So the constant here depends on energy, right? Here we had the uniform with C, the locally uniform in energy. Right? Here the constant was the same all over the spectrum, but the spectrum is compact, right? In this case, the spectrum is not compact anymore, the operators are unbounded. So the constant may depend on energy, but locally, on any compact, you can choose uniform constant. Right? For any compact set, you can choose uniform constant. That's something you cannot really avoid. Right. But it's enough. I mean, you localize things in energy. So for the continuous Anderson model. Now, for the Poisson model. Well, for the Poisson model, okay, so this was, again, this was in the case when, for the Poisson model, what is it? So this is minus Laplacian plus the sum of Vx minus x gamma for gamma in Z, where x gamma is a Poisson process. Poisson process. Right? Then the only result that is holding, that one knows actually is the one of Bourgain-Klein, but it was for this model proved before Bourgain and Klein gave the result. So we only have that n of E is log, it's only known that n of E is log Hölder continuous. And this is a work of Hislop, Germinet, Hislop, Klein. When was this? Maybe 2008 or 9. I don't remember whether 2008 or 9. And it is based on a work of Bourgain and Koenig in 2006. But this work was, this is for the Anderson-Bernoulli. So what is Anderson-Bernoulli? It is just, you take this model, right? So this is Anderson continuous. And the omega gamma are Bernoulli distributed. Meaning that probability omega gamma equals 0 is alpha, or it's P, and probability omega gamma equals 1 is 1 minus P. Right? So of course in this case, for the Bernoulli distribution, right, what you see is that the function mu here does not decay. The mu is just a constant, right? You just you compute what it is. Where is it written? Here. You compute what it is. This thing, right, is going to be a constant because when x hits the support of omega 0, you just get p. So it doesn't decay with epsilon. So it doesn't tell you anything about the regularity. Right? This just tells you that n of e is locally, it has jumps that are bounded, right, at most. But it doesn't tell you anything about the regularity. Okay? So, but it is, well, so one of the questions is, does one have something better? You see, remember, what was the idea behind this proof? Behind the proof for the Anderson model, the idea was, very simply said, if you move the random variables, then you move the eigenvalues of your random operator, right? And as you move the random variables, as the distribution of the random variables is continuous, you can move them continuously, right? But here, instead of, if you imagine the Poisson process, you can also move the random variables continuously, right? These are just points in RD that you can shift around roughly the way you want. The main problem is you don't know, even if V has a fixed sign. So in this case, where you assume that V again is positive and V is not identically 0. Right? If V doesn't have a fixed sign, the thing is becoming much more complicated. And I don't think there is a proof up to now if you take V with sign changing. So you take this case, but when you move around the V's, it is not obvious to understand how does this move the eigenvalues, right? How does, if you take a potential, right, minus Laplacian plus V of x minus y, for example, well, obviously because the minus Laplacian is translation invariant, the eigenvalue of this potential, so this is h depending of this operator, right? If you have, for example, a negative eigenvalue where V, so you could also, of course, you can also assume either this or V negative, this also works, right? If V takes only negative values, it also works. That's fine, but it has to be, V has to have a fixed sign, right? So maybe I write it this way, V fixed sign. Here it was the same thing, V fixed sign. So even if V has a fixed sign, what you see is that when you move y around, the spectrum of this one does not move because Laplacian is translation invariant. Right? So it's not obvious how the moving of the potential acts on the eigenvalues, on the spectrum. Right? This is not as simple as shifting, multiplying V by a constant, right? Which is an additive perturbation. Here there is something more subtle. So there is another model, which is the displacement model. Displacement model. So what is this? This is just minus Laplacian plus the sum over V of x minus gamma minus x gamma, or omega gamma here, gamma in ZD. So I draw a small picture. And what you have is you put right, and you move around. So this is the support of the V's if you want, and you move them around. And there is an old result of myself, actually. So you can put the coupling constant here. Well, no, I won't speak about this very old result myself. I'm just going to take this one, right, and assume that V is non-negative, or V non-positive, or V fixed sign. Then in a paper, a joint paper with, what is it? So myself, Nakamura, Loss, actually Michael Loss, Nakamura, and Stolz. And this was in, well, last year, 2 years ago. It appeared, I think, 2 years ago. I think in 2012, I think. I'm not sure actually. It's in Duke, but I'm not sure about the year. Maybe it's 11. Well, we proved that. So we characterized the bottom of the spectrum. So we proved that there exists some E0. So we characterized. One has that the spectrum, the almost sure spectrum of this model looks like this. So you have E0 and then some interval. And this whole interval, E0 plus delta, is contained inside the almost sure spectrum, right? And there is no spectrum here. Right, so it starts at some energy 0 and there is a little interval of energy. And inside, E0 plus delta. 1. Yeah, we assume one has Wegener and the continuity. And what did we assume? We assumed something on omega gamma has with a continuous distribution such that the support of what? Of V of x minus omega x minus gamma minus omega gamma stays in one of the squares, right? We assume that you move your points in such a way that the support of a single potential stays inside the square, meaning that two potentials never overlap. Support and Vx minus beta minus omega beta do not overlap. Actually, it's more precise. No, it's not that they do not overlap. It's just a consequence. Stays in a lattice cell. Right? So you can move things around, just like in my picture, but they stay inside one cell. Right? And okay, and so you have Wegener and the continuity for a small interval at the bottom of the spectrum. Okay. Now, and this again is for V with a fixed sign. Let me think. I don't remember. I don't think, actually the sign did not have any importance, I think. I think there is no, here the sign does not play. No, I don't remember. Well, let's say fixed sign is going to work, but I don't think actually the sign has really any importance. So there are results for the continuous model here. So if you take again the Anderson model, right, continuous, but when V changes sign, then again, if you change omega gammas, because V changes sign, there is no monotonicity, right? So you don't know how the eigenvalues are going to move. Well, in this case, we proved, there was a first paper by myself in '95 where I introduced, and then we worked on this again with Hislop in 2002. Using the same kind of ideas. And what we proved is that one has Wegener and C at the bottom of the almost sure spectrum. Actually, you have a little bit more than that, meaning that you can also go up into the spectrum. There is a region that you can characterize where you know how to prove these things. And what's the idea? The idea is using the vector field method, right? So the idea is to find the vector field so that you can show that along this vector field, the eigenvalues move, right? And the idea in this case is, because of the special form of the potential, is quite simple. It's the following thing. Imagine you want to compute imagine you're at the bottom of the spectrum. So here, this is the E0 is the infimum of the almost sure spectrum, right? Then what you do is the following thing. What you want to understand is, you want to understand H omega minus E, right? So minus so E minus Laplacian so plus V, yeah, I write it this way, omega gamma V gamma, sum over gamma, sorry, minus, going to take this as minus Laplacian minus E plus sum gamma. And what I want to write is, I want to write what is called the Biermann-Schwinger factorization, right? So I just write this as minus Laplacian minus E 1 plus minus 1/2 minus Laplacian minus E minus 1/2 gamma one half, right? And this is going to be perfectly okay if inside this region you are below the spectrum of the Laplacian. Right? Which is something that's going to happen, right, if V changes sign. Okay, if V changes sign, so what's going to happen actually is that if V changes sign, and if I take not exactly Laplacian, but I take here, I change the random variables so as to shift the potential down, right? I'll be able to show that you have eigenvalues below the spectrum of Laplacian. Right? Actually, you're going to be able to show that. It depends on the support of the omega gammas, right? But if, for example, imagine that the omega gammas are supported around, contain 0 in their support, right? Then you can show that E0 has to be negative. If 0 is inside the support of the random variables, E0 has to be negative. Right? You can show, yeah. And so, what you want to analyze, this is a fixed operator, you want to analyze when does this operator have spectrum near -1. But here, if you look at the following vector, so if you call this a gamma, if you look at the following vector field, right? So this is the radial vector field, and you apply it to this operator, you get the operator itself. Right? If you apply this vector field in the omega gammas, you get this one. Why? Because this just means that this operator is homogeneous of degree 1 in omegas, right? If you multiply omega by lambda, you get the lambda as factor out. So this is just homogeneous of degree 1. So that's just the Euler equation for this homogeneity. Okay, so you have this. But what does it mean? It means that if I take, now I'm interested in the eigenvalues, lambda j of omega close to -1. Right? So this translates as if you can differentiate the eigenvalues, right? If they are, for example, simple, then this tells you that when I take this for lambda j of omega, I get lambda j of omega. Right? Which is close to -1. So it's strictly negative. Right? And so this derivative does not vanish. So it means that the eigenvalue, when you move along the vector field, must move. And you can use this to extract a Wegner estimate using the same idea that were used in the Anderson model. Right? And so this gives you a flexibility in the sense that depending on the operator, you can try to find the vector field. Right? This is how actually I proved a long time, more than 20 years ago, that if you take the displacement model, but with a large coupling constant here, there are some regions where you can prove Wegner estimates and then you can prove localization. Right? So, but it's really the idea of finding a vector field such that if you move your random parameters along this vector field, then the spectrum of the operator moves. Right? This is really what you want to understand. Okay, and there have been many more works on this actually. On many equations actually, not only Schrödinger operators, but also the Maxwell equation, also elasticity equations, acoustic equations, right, for all sorts of operators. This is one of the parts that has been studied a lot for many random operators, right, not only Schrödinger. Okay. And it is, because of the remark I made before, it is a very basic quantity to consider, in particular because of this estimate that it gives you an estimate on the probability that you have eigenvalues in some interval, that your random operator puts eigenvalues in some interval, right? That's the first basic spectral estimate, and we're going to see, well, why it's important. So the second thing, the other thing I wanted to talk about today is another behavior of the density of states, which is called Lifshitz tails. what are Lifshitz stays? So again, I thought that that's the limit when lambda goes to infinity of the expectation of the number of eigenvalues of h omega lambda less than e divided by the volume of lambda, right? And one can do a computation. Imagine that I don't have any randomness. I can do the same thing if I don't have any randomness, right? So, we're going to first treat an example, right? So consider continuous Anderson model. Now, what I look at is the following thing. H omega is minus Laplacian plus sum omega gamma v x minus gamma. What I will assume is the following thing. I'll assume that omega gammas are non-negative. 0, the probability that omega gamma be less than epsilon is positive for any epsilon positive. Right? For any epsilon positive, the probability that omega gamma is less than epsilon is a positive number. Right? And I'll assume that V is also non-negative. Right? V positive. And let's take, of course, V not identically 0 and V compactly supported. Well, then one has the following thing. Theorem. For any delta positive, there exists let me think. There exists C positive, or there exists E delta. So first thing one knows, because of these assumptions, one knows that the almost sure spectrum is equal to the half axis, 0 plus infinity. Why this? For the following reason. First, you see, we assume that the omega gammas have a non-vanishing probability to be as close as we want to 0. Okay? So by exactly the same reasoning that we did in the discrete case, one can show that you have arbitrarily large patches, right, inside the space for omega probability 1, you have arbitrarily large patches, or let's say arbitrarily large cubes, where the gammas are arbitrarily small. So within these large cubes, the spectrum of the operator, which is a local object, looks like the spectrum of the Laplacian. It means that if you have, imagine you have a big cube where omega gammas are all less than epsilon. And I take an eigenfunction near eigenvalue E, not eigenvalue E, but that is close, it's a Weyl, right? It's a Weyl sequence for eigenvalue E that lives inside this big cube. Right? Then if you apply this operator, or if you apply the Laplacian, you get almost the same result. So it shows you that actually the spectrum of this operator contains up to epsilon the spectrum of the Laplacian. Right? The almost sure spectrum of this operator contains up to an error epsilon, for any epsilon, the spectrum of the Laplacian. But of course, this operator, because this is non-negative, is contained in the spectrum of the Laplacian. So you get the equality. Right? This is just by this approximation. So it's actually quite simple to write down. It's the same thing. And what one has, if you look at n of E, this is less than for E in 0 E delta, n of E is less than E to the minus E to the power D over 2 minus delta. Okay, what does it mean? Look, it means that the density of states, right? So of course this is non-negative. We already know it is supported in this set, right? But you see that it decays. I'm sorry, there's a minus here. There's a minus missing. It decays exponentially fast with a power roughly d over 2, right? When E approaches 0. So you have very fast decay. If you plot the function, you have very fast decay when you approach the edge of the spectrum, right? So one way there are, we're going to prove this for this model, but it's true for many models actually. I'll come back to this a little bit later. So one way to write this, another way to write this is that if I look at, so this is equivalent to, imagine that I look at the log of n of E, and I take the double logarithm of n of E, I divide by the logarithm of E, right, absolute value, then this converges as E goes to 0 from above to minus the, sorry, this is going to converge to, this is going to converge to minus d over 2. Right, this is equivalent to that. But this may be a little bit more expressive, right, in the sense that it tells you it's the same statement. Right, if I take the double logarithm here and take double logarithm here, I do the right change of signs, right, I get exactly that. I'm sorry, it's not this. I forgot the other side. Forgot the other side, right? It is both upper and lower bounded by this quantity. Right, so this is the statement, so that's equivalent. So let's, before we do this computation, let's first do another one, simpler one. Let's do the computation for what happens for the free Laplace operator. So the spectrum is the same as the one of Laplacian. So what happens? Well, one can compute what is the number of eigenvalues of minus Laplacian restricted to a big cube lambda less than E, right, divided by the volume of lambda. So let's take Dirichlet boundary conditions. Right, we know what these eigenvalues are. Imagine that lambda is minus L divided by 2. Right? So we know that the eigenvalues are given just by, they're indexed by a multi-index, k in n star, because you have Dirichlet to the d in d dimensions. And this is just pi divided by 2L squared, sum over kj squared, j equals from 1 to d, right? The eigenvalues, ek, let me write it just with a subindex. So I don't index them with a single index, I just take a multi-index, and the eigenfunctions are the product of signs, right? And so we need to compute. So this is equal to the sum, the number of k's in n star to the d, right, such that the sum j equal 1 to d kj squared is less than E times 2L squared divided by pi squared divided by 2L to the d. So you have, I do it in two, I draw the picture in 2 dimensions. So I have the 2-dimensional lattice, right? I only count the points that are both, that have coordinates that are integers that do not vanish. And then I count the number of those points inside a ball. So what's the radius of this ball? The radius of this ball is square root of E divided by pi times 2L. Right, that's the radius of the ball here. And I count the number of integer points in there. Right? But just by simple comparison with integrals, we see that this number corresponds, it's the same thing as the volume of the ball, right, intersected with the quadrant, right, because you're looking just at positive things. So this exactly behaves like, so this in the limit, when you let L go to infinity, right, behaves like, well, you take the volume of the ball, so you have E to the D over 2 times a constant, which is the volume of the ball with the pi's and the fact that you only take 1 over 2D, right? You have 2D quadrants and you just look at one quadrant. Okay? You're just looking at the quarter in 2 dimensions of the quarter of the plane, not at the whole plane. So it behaves like this. Okay? So we can compute, so N of E in this case is computed exactly, and it has a closed formula, which is just this. And you see that it also vanishes when you go to the extreme of the spectrum, but in a much slower way than for the random case. Okay? So this phenomenon was first seen by, as the name tells, by Ilya Lifshitz in the 50s. In the 50s, and it is actually very important. It is the first, it's more or less the first thing that is linked to localization, right, for random operators. Okay, let's prove it. We're going to see what happens.
Looks like this estimate is for big energies.
But this is for any energy. That's an equality. It's held at any energy. It is true, of course, for large ones called Weis law, right? But it is true when you go to the limit and look for the Laplacian, this is correct. The constant depends on the dimension. This is correct at any energy. Of course, for E positive, for E negative, it's 0, right? There's no spectrum below 0. But this is correct at any energy. Okay? And here we're interested in what happens near 0, right? Just to compare with this one. Okay, what's the difference? Okay, why does one get this exponential decay? The idea is the following. So the first thing is, we know that if we look at the eigenvalues of minus Laplacian plus of h omega restricted to lambda with Dirichlet eigenvalues, with Dirichlet boundary conditions, less than E, just because of Dirichlet-Neumann bracketings, the Dirichlet eigenvalues are above the Neumann eigenvalues, right? We're going to compare Dirichlet and Neumann. Dirichlet eigenvalues are above the Neumann eigenvalues. And moreover, you know that if I take, let me draw the picture in 2 dimensions. If I take a volume lambda and divide it in 2 pieces, lambda 1, lambda 2, right? Then you have that minus Laplacian restricted to lambda 1 plus minus Laplacian restricted to lambda 2 with Dirichlet is above minus Laplacian restricted to lambda. So lambda is the union. Right? Which is, so this is what is called Dirichlet-Neumann bracketing. Minus Laplacian restricted to lambda 1 with Neumann. Right? For the Laplacian, we all know this Dirichlet bracketing, Dirichlet-Neumann bracketing, right? But this will tell you that if you compare the number of eigenvalues for the Dirichlet Laplacian, right? So this is actually, here we can take Dirichlet, and here we have another one larger than Neumann on lambda, right? So this will tell you that you have this less than number of eigenvalues of h omega lambda with Neumann less than E. Right? Okay, we have this. And this does not depend on omega. The potential doesn't change this. Okay? So if we do now take the expectation here, this is going to stay true. But in the way you prove actually that this converges, right, shows you that if you look at the density of states, it's going to be in between the two. The density of states times the volume, right, is going to be in between the two. This is because what you're going to show is that if you look at this one without the expectations, this is going to be an ergodic process, right, which is superadditive. And this one is subadditive because of this. Right? And so what you'll have is that these two ergodic processes will converge. You have to prove that the limit is the same. But then one thing that is sure is that we know that this thing is going to be in between the two. Right? So one has this basic inequality, okay, that I won't prove, but that comes from Dirichlet-Neumann bracketing. Okay? And now the idea is that, well, using this for small e, we can estimate these two things, right? For any volume, we just need to choose the right volume. Okay? So let's do the lower bound first. The lower bound. So let's prove the lower bound. Oh, actually, what I am sorry. If I want to have this lower bound, I need one more assumption. I need something more precise than that. Yeah, there are two ways. So the upper bound I wrote was correct, but I was a bit too fast. If I need I want the lower bound, right? What I need is something. If I want this lower bound, exactly this one, right? I need an assumption on this thing. What I need to, for example, one assumption I need, this is not enough. This is not going to be enough. Okay, we will see in the proof why. We need an assumption on this, and what is this assumption? It is just, for example, imagine that the log of P omega gamma larger than, less than epsilon divided by, let me think now. What do I need? I want this probability not to be too small. That's one thing. I need this probability not to be too small. So let me think. Let me think. There are many ways you can phrase this. I want this not to be too small, so if I take the logarithm, right, divided by, so I take double logarithm. So roughly what I want is that if I take the double logarithm divided by the logarithm of epsilon, right, this goes to 0 when epsilon goes to 0 from above, right? Assume this to get star. So star is the lower bound, LB. Let me call it LB upper bound. I need to assume this. You're going to see why in a second. The upper bound is the most important part, but the lower bound has its own use. But you need something like, you need some equivalent to this, but this is actually optimal. So what we're going to do is do the following. So let's take a cube. So fix E. Small. And let's take a cube lambda, which is going to be lambda of L, where L is just e to the minus 1/2 minus delta. So fix delta positive. It may not be the same as in the statement of the theorem, but it's going to be close to it, right? And fix this cube. Okay. And then what we know that n of E is larger than 1 over the volume of lambda times the expectation of the number of eigenvalues of h omega with directly boundary conditions on lambda less than E. Right? But now we're going to go to get an estimate for this probability. Right? But this thing is certainly lower bounded by 1 over lambda, the probability that there exists an eigenvalue of h omega directly respect to lambda less than E. Right? And to get an estimate for this probability, you just need to choose omega gammas in a proper way such that you can create such an eigenvalue. Right? That's the only thing you need to do. To get an estimate, a lower bound on this probability, you just need to construct a set of realizations on which this condition is satisfied. Well, so what do we know? What do we know? Look, you take h omega d restrict to lambda. So this is minus Laplacian lambda with directly bounded condition plus the sum of omega gamma v x minus gamma. Gamma in, well, gamma is not exactly in lambda, right? So we restrict, lambda gamma is in zd restricted to lambda. Let's assume that v has, I said v has compact support, right? So this actually is going to be the only zd we're going to see is just the gammas that are in lambda plus some ball of center 0 radius r, right? We need to increase lambda somewhat, okay? And that's the only ones that we see because v has compact support. We don't see any potentials outside there, right? So you see a few potentials that are sitting outside if the support is large enough, right? But you don't see the next one. So this is just, you have this, okay? And now, what is the lowest eigenvalue of this? What's the ground state of this one? Well, as we said here, the ground state, what is the ground state? The ground state is nothing but what do we have? Dirichlet, so it's pi squared d divided by L squared, right? You take each dimension, you take the ground state for each dimension, so it's 2L actually, I took lambda L, so it is 2 L squared, right? Which in our case is equal to pi squared d squared, so it's a constant. It's e to the minus e to the 1 plus 2 delta. Okay, this ground state is much smaller than E. Okay, now, and we know what the ground state function is. It's just the product of the sign pi x j from 1 to d divided by 2L, right, and normalized 1 over, you have a constant divided by square root of L, right? So that's the ground state. That's the ground state energy, and that's the ground state. Okay? And now if you arrange, when you take this V omega lambda, if V omega lambda, right, is also applied to phi 0, scalar phi 0, is less than, well, what do we take? For example, E over 2. Right? This in particular is less than, this is much smaller than E over 2 also, right? Because it's, E is small, so the E to the 2 delta is small. Then we are happy then there exists an eigenvalue of h omega lambda less than E. Right? Because we know that we have a test function such that the quadratic form applied on the test function is less than E over 2 divided plus E over 2, meaning E. So what does this mean? But if you compute this using this function, what do you get? You get that this is roughly, so if you have this. So now we want to compute this. What is V omega restricted to lambda phi 0, phi 0? Well, this is certainly less than a constant divided by, here the product should be, this is inside, so here. This is square root of L is inside, right? So once you get it out, it's L to the D over 2. Right? For each sign, I have a square root of L, so it's L to the D over 2. So I get L to the D, right, times the sum for gamma in lambda plus the ball 0 R. And I integrate, so I get omega gamma, and I integrate V against this, right? V against phi 0, that's another constant. So you get this. Right? And so if you take, for example, all the omega gammas, if for any gamma, for all gamma in lambda plus B 0 R, right? We know that omega gamma is less than what? Than E over 2 C prime. Then this will be bounded by, E over 2 C prime. Then this will be bounded by, so how many points do we have? So for L large, this is going to be bounded by C 2L to the D E over 2 C prime divided by L to the D. So I take 4C and I get 4C. Right, this goes away, goes away, goes away. Over 2. Right, C is just a constant that's here. Right, I just take this event. I imagine that inside this big cube, all the omega gammas are less than this. Okay? So what's the probability of this? Well, the probability of omega gamma, the probability of this event, so if omega belongs to this thing, which I call omega L, well, it is just the probability of omega gamma being less than 4C, right, to the power, the volume of the cube, so it's bounded by from above. And here again, I bound the volume of the cube by 2L to the D. Okay. Right? You have this estimate. Just bounding the volume of the cubes by something larger, so you just take all of these are less than 1, so it gives you a lower bound. And now, we're going to need the assumption I put down there. Right? Because of the assumption I put down there, we know that for any delta, the probability that omega gamma be less than E than epsilon to the delta, this is larger than epsilon, is larger than E to the minus epsilon to the minus delta. Right? That's exactly the assumption I've put here. If I take the double logarithm, you see, if I take double logarithm, what happens? First logarithm, this goes away. Absolute value, this goes away. Second logarithm, you get minus delta times epsilon. Then minus delta times log epsilon. You divide by log epsilon. It leaves you minus delta. The fact that this goes to 0 means that you can get the delta as small as you want here. Okay? So we get, if I call this, we get that probability that omega is larger, belongs to omega L is larger than e to the minus, so I forget about the constants by just changing the delta for e small, e to the minus delta, right, comes here, and this to the power multiplied by L to the d, which is e to the minus d over 2, and we had, it's up there, e d over 2 times 1 plus delta. Right? Because I took L to be of size minus 1/2 minus e to the minus 1/2 minus delta. And so this is e to the minus e minus d over 2 plus d over 2 plus 1 times delta. And now we change delta. Right, you replace, call delta, this is delta, because the delta can be as small as you want. Okay, and you get the claim I have here. Right, you get the claim I have here. Now you see that if this would decay faster, there is no such bound, right? So to get the low bound, this assumption is important. Otherwise, this probability may be much too small. Okay? But this method, to get the lower bound, you just need a test function, and it always works. To get the upper bound is slightly more complicated. Okay, to get the upper bound. Therefore, we're going to use the Neumann part, right? What do we know? We know that, so we're going to choose lambda again, but now I'm going to choose L equals e to the minus 1/2 minus delta. So I choose a cube that is slightly smaller, right? And what I know is that n of e, by the same reasoning, right? Well, you need a little bit more. You need a little bit more. So we know that by our assumption, as v omega is uniformly bounded by a constant, right? It's not really necessary, but it's simple. It makes it simpler. We know that the number of eigenvalues of h omega, well, actually, what's the only thing we knew as we just need v to be positive. It doesn't need to be bound by a constant. As v omega is non-negative, we know that the number of eigenvalues of h omega Neumann boundary condition to lambda less than e is bounded by the number of eigenvalues of minus Laplacian less than e, right? So it is bounded for sure, and this is for any omega. It is bounded by a constant times the volume of lambda. That's the only thing I want. Okay, it's bounded by a constant times the volume of lambda. And then what we have is that, well, this implies that n of e times lambda is actually less than what? Less than this constant times lambda, the probability that h omega n lambda has an eigenvalue, or there has eigenvalue less than e. Right? Why? You just write the following as the number of eigenvalues of h omega lambda n less than e by this inequality, right, is bounded by the characteristic function of h omega lambda n has eigenvalue less than e, multiplied by exactly this constant, c times lambda. Right? Because this is 0 if this, when this is 0, right? And when this is 1, then we know that this bound is correct. So and then you take the expectation of this, gives you the expectation of this, but the expectation of this characteristic function is just probability. Right? And so the lambdas go away, and you get this bound. N of E is bounded by the probability to have an eigenvalue less than E. So you see it's roughly the same type as before, except for the fact that we don't have the 1 over volume in front of it, but it doesn't really matter. At this level of precision, it doesn't change anything. Okay, now, so we're going to estimate the probability that h omega lambda n has an eigenvalue less than E, right? And as I said, we choose L to be E to the minus 1/2 plus delta. Okay, so what do we know about the spectrum of this? So if I look at minus Laplacian plus V omega restricted to lambda. Oh, so first I look at consider minus Laplacian restrict to lambda with Neumann boundary conditions, right? On a lambda L. So what's the ground state? So ground state energy is, well, what is it? It is 0, right? And what is the ground state? For Neumann Laplacian, it is 0. And the ground state is 1 over square root of its constant function, 1 over square root the volume of lambda L, right? For the Neumann thing. And what is the first excited state? First, so meaning the first eigenlevel, right? The first eigenvalue which is not 0, above 0, well, it is 1 over, so it is pi divided by L, pi squared divided by L square. Which 2L square, sorry. So it is of order e to the 1 minus 2 delta. Right? It's of order e to the minus 2 delta. So it is much larger than E. Right? We are interested in the eigenvalues below energy E. So this is much larger than E. Okay? So now, as pick phi, such that, imagine that you have an eigenvalue. I want to estimate, I want an upper bound on this, right? So imagine that I have an eigenvalue below energy E. Pick phi such that h omega lambda n of phi, scalar phi, be less than E phi squared. So I'm going to normalize phi. Be less than E. What does it mean? It means that gradient phi squared plus V omega lambda L phi be less than E. Right? But this one is positive. And this one is also positive. So it means that at least both are at least less than E. Right? Because the two quantities are positive, the sum is bounded by E, which is non-negative. And so we have that both are positive, are bounded by E, times the normal phi squared. Well, what we're going to do is, we're going to use the first estimate here to get some characterization about who phi is. So let phi, right, phi 0, so let phi equal a constant, right? So this is just a constant function. I call it alpha, so I should see it as a constant function. So you should see it as alpha times phi 0, right? If I call this phi 0. This is alpha times phi 0, right? I should normalize the constant, so let me write alpha times phi 0. So this is a constant function, plus phi orthogonal, where of course phi orthogonal, scalar phi 0, is 0, right? It's orthogonal to phi 0. And then if I look at minus Laplacian Neumann restrict to lambda phi scalar phi, well, this can be computed, right? It is just equal to, well, the first term disappears. It's just minus Laplacian lambda n phi 0, phi orthogonal, right? This is just because the orthogonal space to the ground state is an invariant subspace, right, for our self-adjoint operator. That's all. But this now, we know is larger than what? Well, we know that the lowest level above the ground state is larger than this. So this is larger than e to the 1/2 minus delta squared. Right? Because the spectrum of this operator, restricted to the orthogonal to the constants, right? Its lowest energy level is of this size. So it's larger than, what did I say? Than maybe a constant there is for some c. And the constant is actually computed. Here it is.
Why 1/2? There is 1?
Oops, sorry, yeah, there is 1, exactly. It's not 1/2. I miscopied. 1 minus delta, that's correct. Exactly, that's it. But this, on the other hand, is less than e. So it tells us that actually what is falling on this thing, right, is small. It's less than c e to the, sorry, there is a what do they want? Yeah, e to the 2 delta, right? So I get this as less than e to the delta. So most of the vector phi, right? Most of the vector phi here is on phi 0. Right? My vector phi is very close to phi 0. Okay? And then if I compute now v omega restricted to lambda phi phi, what do I get? I get that this is v omega lambda phi 0 plus 2 real v omega lambda phi 0 phi orthogonal plus v omega lambda phi orthogonal right? But v, my potential is bounded, right? So this is actually bounded by c e to the delta. Right? This is bounded by c e to the delta. And what else do I know? Well, here I can I use the same idea. Delta 2 delta, actually. Here I use the same idea, right? I split things. So this is also bounded by c. What I can do is I can use the fact that it's positive, right? To say that this is less than alpha v omega. So this is less than, sorry, this is larger than minus alpha, so fix alpha between 0 and 1. So this is larger than minus alpha v omega lambda phi 0 plus 1 over alpha, right? V omega lambda phi orthogonal. Right, you certainly have this. Okay, this is just because A, B, right? You just smuggle, sorry. Okay, you just smuggle a square root of alpha and 1 over square root of alpha in here, and you get what you want, right? By the usual thing, a plus b squared is. Okay, and what do I get here? Well, I get the following. Oh, I get that this is larger than 1 minus alpha. V, so this is just, what is this? This is just the integral of V omega lambda over lambda divided by the volume of lambda, right? dx, by the definition of phi 0. Phi 0 is a constant, right? Plus 1 minus 1 over alpha, V omega lambda square, right? So this is of order, as I said, C e to the 2 delta, right? And I get that, finally, I take alpha equal 1/2, and I get that 1 over lambda volume has to be less than C e 2 delta. Right, for a new constant C. This one is less than E, so I put the delta on the other side. Delta is small, so this is the main term. And sorry, this here what I write is of course an absolute value. This is larger than 1. I mean, it's less than, sorry, it's less than 0. It's not larger than 1, it's less than 0. Okay, 1 over alpha is larger than 1, so this is less than 0. Okay? So, what do I know? What did I prove right now? Well, I proved that the probability that H omega Neumann to lambda has eigenvalue less than E is bounded by the probability that the integral 1 over lambda V omega lambda x dx be less than C e to the 2 delta. Right? But now, this integral, well, we can do the following. It's certainly less than, sorry, it's certainly larger than the sum for the gammas less than L over 2, right? I just have the big cube, and then I have a smaller cube, so this is L over 2, this is L, right? And I just keep the points that are in there because the V's have compact support of what? Of the integral of V of x dx omega gamma, right? And this is the integral over a whole of Rd. Right? And this is just a constant. Okay? So in this way, using this is a constant, I get that this probability, the probability here is less than the probability that the sum for gamma less than L over 2, 1 over L to the D of omega gamma is less than C with a new constant C 2 delta. Right, I just changed the constant. You have this constant, put it on the other side. And I change the volume from here is 4L, right? I get rid of the 4 and put it on the other side. Right? So we need to understand this. But what does this look like? I have IID random variables. And I take a large number of them, and I compute the empirical mean. What does this converge to? This, by the law of large numbers, converges to the expectation of omega 0, which is positive, right? These are non-negative eigenvalues, they're not trivial, they're not 0. by assumption. We know that the probability that they are positive is non-zero. Right? So you see that when L gets large, this will almost never look like, it's not going to be smaller than this, because E, if you choose it small, is going to be much smaller than this. Right? Remember, E is small. So this is what is called large deviation estimates, or large deviation estimates in probability theory, and let's estimate this probability. Well, the way to estimate this, we're going to use what is called Cramer's method. Yeah, I think it's Cramer. It's just the following thing. We know that. So let me call this number omega bar. It's just simpler to write. And fix. And let's estimate. Right? What I'm going to estimate is, so this is certainly less than, for E small enough, the probability that 1 over L to the D sum of gamma less than L over 2, omega gamma is less than omega bar over 2. Right? Let's estimate the probability that this be less than, if E is small enough such that this be less than omega bar over 2, you get this inequality. Right? Well, how do you estimate this? But what we write is that the probability that 1 over L to the D sum of gamma less than L over 2, omega gamma less than omega bar over 2, this is bounded from above by the expectation of E to the minus, of E to the minus, let me think. E to the T minus 1 over L to the D sum of gamma less than L over 2 omega gamma. Right? Why is this correct? This is because this is just, that's the expectation of the characteristic function of this set. Right? And here we are saying that the exponential here is larger than the characteristic function of this set. If this inequality is true, the argument in the exponential is larger than 1. Right? So E to the argument is larger than 0, sorry. If this is true, the argument inside the exponential is larger than 0. Right? So E to this argument is larger than 1. If this is false, then the characteristic function is 0, and the exponential is always non-negative. Right? So this is just the fact that this is just as characteristic function of this set is less than this exponential. It's just this, right? And then you take the expectation on both sides. And this is true, of course, if t is non-negative. If you take t non-negative, right? But this side, we can actually compute, because we know that the random variables are IID, right? The random variables being IID, this is equal to e to the t omega bar over 2. Okay, times the expectation of e to the minus 1 L to the D of omega 0, whole thing to the power, this thing to the power L over 2 to the power D, the volume of the cube. L to the D, sorry, not L over 2. And to make things simple, I'm going to assume that my omega gammas are bounded, right? Omega gammas, I assume that they are bounded random variables. But because they are bounded, we can, oh, sorry, there's a t here. There's a t. Okay, we can do because the omega gammas are bounded, we can compute this. What is this? This is, I can do a Taylor expansion of the exponential, right? What do I get? I get 1 minus t L to the D times, so I do a Taylor expansion for this thing, 1 minus t to the D omega, expectation of omega 0, which is omega bar, right? Plus t over L, t square L to the 2D times a constant, right? This is, this is not actually, this is this, okay? I can write this in the following way. I can write, actually, I just need an upper bound. I write that this, right, is smaller than this. Just by doing, or if you want, which this is something I can rewrite in the following way. I write this directly as an exponential. It's going to be simple. This, because of this, right, it's going to be less than e to the minus t divided by L to the t omega bar plus a constant times t squared divided by L to the 2d. Just by doing a Taylor expansion, right, for this. I just do a Taylor expansion for the exponential. Okay, and this is going to be correct if t is less than epsilon times L to the d. As long as t is not too large, right, t over L to the d is going to be small, right? And you can do Taylor expansion and get this result. So we get that what we're looking for, let me call it P of L. P of L is less than e to the t omega bar over 2 times, e to the minus t, well, this one kills half of that one, plus c t squared L to the d, 2d times L to the d, so this goes away, so I have t squared L to the d. Right? I get this. And now I see that if I take t is, we choose, so take t equals epsilon L to the d over 2. What do we get? We get that this is less than e to the minus omega bar over 2 times epsilon plus c epsilon, sorry, I'm going to put the epsilon here, minus epsilon L to the d over 2. Right, I can choose the t as long as this is not too big, right? But if I choose t like this, divide by L to the d, it's going to be small. So my Taylor expansion is perfectly fine. Okay, and now pick epsilon. C epsilon equals omega bar over 4. And you get that this is less than e to the minus some constant kappa times L to the d over 2. But remember what L was. This is e to the minus kappa, e to the minus, I need to do something better than that. I'm not going to take L to the d over 2, I'm going to take L to the d. Sorry, I take L to the d with epsilon, I take L to the d, so I get here L to the d, that's fine. I don't see what I did L to the d over 2. Because you see, if I did this, I get L to the d is fine, not L to the d over 2, it's L to the d. Right, this is fine, and take L to the d, because here what I did is taking L to the d. Right? Otherwise, if I take L to the d over 2, this goes away, this is constant, and this is big. But what I want is these two terms to be roughly of the same size, just the negative part should cancel. Right, it should kill this one. So I take L to the d with epsilon small. I take this much smaller than omega bar. Up. This, you get this, and so you replace L by its value. What was it? It was minus d over 2 plus d times delta. Right? And you get what we expected. You get that the probability is e to the minus constant d over 2 plus delta. Right? So you get, maybe I erased, did I keep it on the board? No, I erased this. This was on this board. Right? This is what I wanted to get. Any question?
Where did
Oh, this is because what is the first term? This is 1.
No, the second. Then the second.
This one? No, this one, if you take L to the D, the L to the D goes away, right? And you have T omega over 2 and T omega bar. So this gives you the minus T omega bar over 2. Right? This is where it's cancelled with the other one. Right? Okay, so we get what we wanted, right? And the whole point is now, you see, before we had this assumption on the fact that the probability that omega gamma be small does not decay too fast, right? That this doesn't get small too fast. If it gets small very fast, you see that here actually this estimate can be improved, right? You can improve this because what you do is you don't replace e to the 2 delta by this. You keep e to the 2 delta, but e is going to be small. So you get that the probability that this average be small is actually much smaller than just this term. You get this way, you can incorporate the fact that the distribution of probabilities, right, has a very fast decaying tail near the edges of its support. Right? This is the simplest way to prove it, but it's not the most efficient. Right? It's not the most efficient. So we proved this for the Laplacian. What does it mean? Where does it come from, actually? What's behind this? The heuristic picture behind this, now we got the proof, actually is contained in the proof, is the following. So you have your random landscape. And this is the 0 level. So I assume that my potential is, I should have drawn the 0 level first. Right? Imagine you want to have a low-lying eigenvalue. Where can you have a low-lying eigenvalue? Well, the only regions where you can have low-lying eigenvalues is when the potential is small. Right? As soon as the potential is not small, because it's non-negative, the eigenvalues cannot be very low. So regions where the potential is small are the only regions in space where you can have low-lying eigenvalues. Right? But these regions, by large deviation principles, exactly what we had here, tend to be pretty rare. Right? Because if I have here, for example, if I had here in between another bump like this, right? If the region is not small, then what you do is it more or less splits this region into two and it increases the eigenvalue by a non-negligible amount. Right? So you really need the regions in a way to be connected. Not exactly in higher dimensions, it's not exactly a connected region, right? You don't need something like, but nevertheless, right? If you have two regions far apart where the eigenvalues are small, where the potentials are small, but these regions are not too big, it's not going to create a very small eigenvalue, right? So that's the basic philosophy. Okay, so I'll come back to this picture in 5 minutes, but I want to do something before that. So actually, what is known for Lifshitz states? So this is also a topic that has been studied a lot. And it is of interest not only for random Schrödinger operators, but it's also of interest for probability theory, especially people that study random walks in random media, right? Because these Lifshitz states are well related immediately to the, so let me remember what it's called. No, I can't remember the name. Well, there are, I don't remember the name. There is a quantity which is the name of which I don't remember, but they're directly related to the way Brownian motion in a random, right? Brownian motion in a random obstacles, right, is actually its generator. The generator of this process is actually a Schrödinger operator with a random potential, right? And the path, I mean the Brownian motion, right, defines a measure of a path in whole space, and where this measure puts weight is directly related to these Lifshitz states. Right? Actually, Lifshitz states is some integrated version of that. So what does one know about Lifshitz states for more general situations? Actually, roughly the philosophy is that Lifshitz states occur at all spectral edges, so all edges of the spectrum that are unstable and potential perturbations. So what does it mean? What does it mean? It means, for example, the following. If I take the following example. Let me just, let's take the following example, which is not a Schrödinger equation, but it's actually it's simpler to understand for this example what I mean unstable. Take the example h omega is minus gradient 1 over rho omega, or v if you want, v omega plus 1 gradient, where v omega is just the usual Anderson model, and we assume that the v gamma is positive and omega gamma are also non-negative, right? So I can look at this nice operator. Okay, that's perfectly well defined. And what you see is that the spectrum, of course, by the very form of this quadratic form, the spectrum of h omega is equal to 0 plus infinity. Well, actually, no, maybe not 0 plus infinity. There may be some gaps inside, but one thing is sure, is that it contains some interval 0 delta, right? And this is true for any values of v omega. And if I change v omega, the fact that 0 is inside the spectrum, right? And of course, it doesn't contain any negative values. Spectrum of this operator doesn't contain any negative values. And what happens is that 0 here is a stable edge, because whatever I do with the potential, it does not change 0, right? I can do, because the 0 comes from the fact that constant functions are annihilated by the gradient, right? If I apply a gradient to some constant functions, I get 0, right? And this is why 0 is inside the spectrum. But actually, the one thing I should have, the example I should have taken is okay, so that's what is stable edge. But if I look at minus Laplacian plus sum of omega gamma v gamma, right, with the same assumption on omega, same as so omega gamma non-negative, v gamma non-negative. Well, imagine that 0, right, is in the support of omega gamma. So then we have seen that the spectrum starts at 0 here, but here 0 is unstable. Because if I move the potential, imagine that I move all the omega gammas a little bit up, right, by the amount epsilon, then the spectrum will start at epsilon, right, times some constant because of the v, right? You shift the spectrum. This spectrum here, the edge, is sensitive to the changes in omega. So there you expect Lifshitz states. So, and so it was proved for, well, the Lifshitz states will also say, there's another thing which is maybe less obvious. If you look at the displacement model, well, in the paper I quoted before, we know that there are Lifshitz states were proved at the bottom of the spectrum. For the Poisson model as well. Actually, that's one of the first models for which Lifshitz states were proved, the Poisson model. What else do I want to say about this? And it was also proved that if you look at the following thing, if you look at now continuous Anderson, and take minus Laplacian plus sum of omega gamma v x minus gamma plus w, where w is periodic. Then the spectrum, imagine that omega gamma, they take values in an interval. Then one can show that the spectrum sigma, the spectrum of this operator, the almost sure spectrum, one can show that it has a band structure. And from some point on, there is just, the band is just one band that goes off to infinity. So this is in dimension, actually this is correct in any dimension. This picture is correct in any dimension. The band structure, and the band goes to infinity. So let me, I'll write just a case. Band structure. All right, and so if you assume that then one has the following result. So consider the following. Consider HA and H, or H of t, to be minus Laplacian plus W plus the sum of t v x minus gamma. So t in front if you want, sum over gamma. Okay, so this is a periodic operator. Right? And you look at t going from A to B. So I just draw it. So you have E0, E1, E2, E3. So I call it E0, E0 minus, E0 plus. E0, E1 minus, E1 plus, E1, E2 minus. And then we have the following theorem. So that's a result of mine in 97. Assume that, I need an assumption on this. Assume, actually I'm going to call this HA, I'll call H minus, and HB I call H plus. Right, for the maximum value of A of t, which is B here, is H plus, and the minimal is HA. And assume, on the random variables, assume that the probability that omega gamma minus A be less than epsilon, right, is little o, no, is larger than e to the minus epsilon to the minus delta for any delta positive and epsilon small. And the same thing for B. Right, so it's the same thing. The probability distributions do not decay too fast when omega is close to A or omega is close to B. It's the same thing as we had before for A equals 0. Right, same condition. Then the theorem is the following. Then for sigma equals plus minus, and one has the fact that the logarithm of the density of, so the logarithm of the density of states of n of E minus n of Ej sigma, so J is any of these bands, divided by the log of E minus Ej sigma, tends to d over 2. The fact that this limit is equal to d over 2 when E goes to Ej sigma and E staying in the spectrum is equivalent to the log of n sigma of E minus n sigma of E j sigma divided by log of E minus EJ sigma, so modulus, modulus, modulus. Right here we have modulus also because we don't say which side we come from, so it could be positive, it could be larger or smaller, depending on whether you're from the right or from the left, tends to d over 2 in the same limit. Right? And what is little n sigma? N sigma here, this little n sigma, is the integrated density of states of H sigma. So you look at the periodic operator, H sigma, you have two periodic operators, where omega is either minimal or maximal, right? And you have a Lifshitz stays with exponent d over 2, if for the random operator, if and only if you have the standard. So what does this mean? This means roughly that if you look at n sigma minus n sigma ej sigma, this is of order e to the minus ej sigma to the power d over 2. Right? So the random operator has a real Lifshitz stays with exponent d over 2, if and only if the corresponding periodic operator behaves like it would for a free Laplacian. Right? Remember, for the free Laplacian, we saw that the density of states at 0 behaves like constants e to the d over 2. So we say that in the general picture, you still have this. But this one is not always the case. Right? That's more complicated in general. Well, actually, I should be cautious. It is not proved that it's not always the case. Right? And when those examples that are not Schrödinger equations, for which it is not the case, but there is no, to my knowledge, proof. It's an old problem for periodic operators to understand what happens to the Floquet eigenvalues at band edges. Right? It's an old it has been open for 50 years, right? To know what is happening, for example, to prove that for a generic periodic operator, Floquet eigenvalues at band edges have quadratic non-degenerate behavior, right? This is an open problem. It's an assumption that is used very often when dealing with periodic problems. It is known to hold for the bottom of the spectrum, but inside it's not even known for a generic periodic potential, right? Okay, so next time, well, I'm going to stop here, and next time we'll speak of localization, right? So on Monday, tomorrow, day after, no, 3 days, I'll tell you about localization, and then after the holidays, we'll come back and do spectrostatistics.